So yesterday we talked about the concept of current, right? Now, let's go back to the analogy we made in the beginning of class. It's a simple mechanical analogy. The idea of like water flowing through a pipe. So the current of the water itself being similar to the idea of the charge carriers traveling through a metal wire, delivering charge or electricity or power to different devices. Today we're going to talk about resistance, but what are some things that would cause resistance for other types of flow? For example, for like water flow. What would cause resistance for water flowing either down a river, through a pipe? What's an example, Alejandro?
Maybe like rocks.
Rocks.
In a river, a small river.
So some sort of objects?
Yeah, objects. Or like maybe you flush something down the toilet that's not supposed to be flushed, like a toy.
Exactly, it's stuck in the pipe. Okay, what else? You're absolutely right, it's objects.
I don't know if this could be considered something, but like if a river flows a certain way, because like I feel like if it's flowing straight, like for a really long time, it's easier to flow, but then the water has to like change direction.
Okay, so when it turns, what do you notice? There's more what? When something like would turn around on the bank, it'd be as a result. Like if a river was flowing like this, why does it? Yeah, you would have like either more friction or you'd have more contact. It would be like more turbulent, the water itself. So changing of the orientation.
I'm thinking of just forces like wind, maybe like wind or something. Because if you're like running and the wind's, it slows you down. Or I was thinking skiing-wise, because if you ski in the wind, it'll actually slow you down.
So an external force
Yeah.
pushing it along. A good idea there, like pressure head in a flow of a pipe. If you have a pipe that flows down or angled down, and you pour water in it, the water's going to come down automatically. What force is pushing it along? Gravity. Yeah, it's the one that you don't always think of because it's not a contact force. So forces that are acting externally. Anything else you can think of that would resist flow? These are good examples because we're going to use these ideas today. All right, so now we take that concept and we talk about with electrical circuits that we want to control the flow. Just like with any sort of piping system. You don't want the flow to be abundant. Do you want to turn on your sink and the water to spray everywhere? No, obviously not. So you have different things along the way that are called barriers. So for example, when I turn on this sink over here, at first no water's going to come out. It's going to take a second to move, and a very little bit will start to stream out at the bottom of here. Only a little bit, not even at this point. There we go. Only a little bit comes out here because there's a little bearing inside of here that opens like a gate, usually called a gate valve. And that gate allows a little bit of water to pass through. Imagine here's like like an actual like gate of like a castle, And there's imagine the castle is filled with honey, I don't know, some fluid. And you start opening the gate like this. Wouldn't it start to flow out the bottom like a little bit at a time? And then when you open the whole thing, it's like opening the floodgates. Have you ever heard that saying before? We're going to see that with resistance, with electrical resistance, it's the same concept. You want to control the flow. In any sort of fluid flow, the idea is that you don't want this to be overbearing, but at the same time you don't want the flow to be trickling out. How many of you have ever gotten into a shower before where there's like no pressure at all? It's like a weird feeling, right? The water's just it's like just dripping on your head. You're like, it's not even any water coming out of it. Or, like you can't even get the soap off your body. So that would be not really good control of the flow, right? It would be like the flow would be staunched. It'd be stopped too much, right? It would be resisted too much. Versus obviously, has anyone ever been in a shower before where honestly it's like too much pressure? Yeah. It almost hurts. Hit your body. Hit your head, your back. It's not comfortable at all. So the idea in this section is to find the perfect amount of flow. And the way you can do that is by using what are called resistors. So this whole concept of resistance is like controlling the flow at different paths or points along the way. So maybe in a piping system you have several locations where you can control the flow. If you've ever done this before, if your folks have ever done it, if a pipe breaks in your house, it's very difficult to stop the water from flowing out. So what do? You go to the source and you turn the valve off. So for example, there's all this water flowing through a broken pipe in the ceiling right now. You're not going to be able to go to the pipe and hold your hand over it. That's like this, you see on this TV show, somebody's trying to stop the flow. It's not possible. Good luck. It's not going to happen. Especially now the water is flowing out. It's going to your hand's going to slip. It wouldn't even be possible. What you do is you find the source of the water flowing to that location and you shut that valve off. So you have these safety valves at several locations along the way with a piping system. Well, here, with a circuit, you're going to have resistors at different locations. And those resistors control the flow of electricity. Without resistors, the flow would be too abundant. Remember how yesterday I talked about what circuit breakers are? If the flow is too much, the circuit breaker senses it. The circuit breaker says, there's too much current going through the system, open the circuit so it stops the current from flowing. It's literally what it says. Just open it up and we don't want current flowing anymore. You need to have a closed circuit for current to flow. Different from water. If you open up the pipe for water, what happens? The water will shoot out. With electrical current, you open up that circuit, it stops the flow automatically. It needs to be contact for it to flow continuously. So here we're going to have resistors along the way. So we're going to talk about the term resistance. We're going to talk about what's called potential difference. It's another word for voltage. And then we're going to talk about what's called ohmic and non-ohmic materials. That comes from Ohm's law. We're going to talk about factors that affect resistance, similar to what you guys gave in the beginning of class. And then the concept of what is called a superconductor. Okay, a superconductor. And we've already gone over that, but applying it to resistance now. So first, resistance, the definition that it should be almost common sense because it's also the same definition for like water flow or anything else. Resistance is, again, something that opposes another thing. In this case, electrical resistance, it opposes the flow of the current. Okay, the flow of the current. So it's something that slows down the current, like a dam. Right? When water flows through a dam, what does it do? It generates electricity in the dam. The water flowing through the dam causes some sort of a crankshaft to turn, which produces energy in a generator, like we spoke about generators real quick. Okay, the same idea with a generator. Well, here, we're looking at the flow in a conductor, or some sort of a metallic item or material, okay, maybe a wire. And now the second term we're going to talk about, you've heard before. Where have you heard the term voltage before?
Batteries.
What?
Batteries?
Batteries. Batteries. I mean, besides batteries, though. I mean, everything doesn't run on batteries, does it?
Generators.
Generators, okay. They have voltage, but more specifically, I mean, think around, like, how many?
You just like open source the electricity that comes out of 110 volts on the wall that I just plug in 120.
Exactly. That's what I was looking at, okay? So voltage has to do with what's called a potential difference. A difference in a potential. When there's a difference in a potential, what's the potential energy of this pen compared to the desk? Well, the pen is a higher potential energy, right? So when I let go, what's it going to do? It's going to fall to the lower potential energy. It'll increase its speed, but the idea is that it has a higher potential energy. All things want to go to no potential energy. That's the whole concept of potential. We talked about potential energy with mechanics earlier in the year. We didn't really get into that idea that the stable point is no potential energy. If I'm sitting on the edge of the table, I could fall very easily, right? Because I have a lot of potential to fall to the ground. But if this pen is already on the ground, it's got no potential energy. It's got no way to lower its potential energy besides moving further down, but it can't because the floor is here. So the idea of potential energy in mechanics relates itself here. So you have this charge that's flowing through a circuit. And when it flows through a circuit, it gains a certain amount of potential energy. Well, if it has a lot of potential energy, as it passes through one of these objects that produces energy or produces some sort of power, it gives up that potential energy. And that potential energy drops until it gets back to the battery or until it gets back to the outlet. But this happens so fast that you don't even obviously know it's happening. So here's our outlets, right? You plug in, the actual charge carrier flows through the circuit. Maybe you plug in your phone, it goes in your phone. The potential energy in that charge carrier gets absorbed by your phone. Gets converted to electrical energy in your phone. Comes back through with no potential energy. Hits the source again. Recharges its potential energy. Comes back out. Your phone takes the potential energy. Goes back in. Recharges it over and over and over again. But at such a high frequency that obviously you don't see anything like this happening.
I don't know if this is relevant, but like how do the different plugs work? So like in other countries they have different outlets.
It's just the shape, honestly. So a lot of the time it has to do with, a lot of the time in other countries you have different specifications like frequency and voltage. They run on different amounts. So that is also true. So like if you go to Europe and you buy the converter, what it's doing is it's converting the amount of voltage you're getting from the outlet. I don't know the exact number, but I think, you could probably look it up. The common outlet in Europe is definitely different in voltage than in the United States. So it's definitely converting the voltage when you use the adapter, but the actual shape of the prongs are really what's different about it.
So it means that like phones will charge faster.
Yeah, but you don't want to, that's the thing. So you have too much voltage, your phone could overcharge, or it could like, not explode, but it could like short it. So that's why you use a converter. Theoretically, it would charge it faster if there's more voltage, etc. Like that's what air conditioner is running on. An air conditioner runs on a 220 volt line. A regular volt line is 120 volts. It's almost half the amount. So your air conditioner needs to draw a lot more power, so it has its own outlet set up for that. It's a different shape and everything on it.
Might be a weird question, but why do some plugs like don't have all three?
Yeah, that's fine. No, it's a good question. Anybody know what the third hole is on the bottom?
To ground plug,
What does that mean?
it means that basically like it creates like more security for the plug, so you're able to like allow for more voltage, not voltage, but it allows for like a third access point.
Okay, you're on the right track with grounding. It's not having to do with access points.
Isn't it for safety?
Yeah, it's a safety mechanism actually.
But like it just can't move.
No, not physical safety, electrical safety. Sorry. It definitely gives it more stability, yeah, that's absolutely true. But that's not really the purpose for it. The purpose for that third, right, we're talking about this right here, right, the weird shape one? The purpose of that is for grounding. Grounding means that like, if hypothetically there was a power surge or there was too much energy, it wouldn't overheat or wouldn't ruin your whatever your appliance is. That actually would take that electrical flow and put it back into the system. Okay, if there was a supercharge of electricity.
My house is from like the 50s originally. It was in the suburbs, so none of them had it. So we have to have adapters for everything to plug into the wall.
Yep. A lot of those are like 2-prong adapters that have a 3-hole.
Yeah, exactly.
But you can just like rip off the.
Theoretically you can, but it's not safe. But you can. I've done that before. Like the third prong, the grounding prong, you can bend it back and forth enough to get rid of the third grounding prong,
Yeah,
and just
I
use the
never
top
done
2 only.
It's done.
If the outlet only
Is
had
that,
2
like,
holes
not
in
a
it and
smart
you had
idea?
nothing else to adapt, you could. But again, you're exposing a random spot in there that you wouldn't want to do it. You're better off getting the adapter, obviously, you know. Now the other thing obviously you can do is you can replace your outlets, but a lot of outlets that only have the 2 prongs, like the house I live in only has a lot of 2 prongs as well. It's an old house from like the 40s it was built. So the 2 prongs at the top correspond to 2 wires in the circuit. Well, there's a third wire that goes into the grounding. So even if you want to put a new outlet in, if your house doesn't have that third grounding wire, you can't actually put the outlet in. It doesn't make sense. You could try to like take that one out, try to reinstall the other one, but you need a grounding wire to actually attach that. Okay. All right, so we're looking again for voltage here, the idea of potential difference. If there's more potential energy in the beginning of the circuit than at the end, you have a voltage drop, meaning there's a lot of potential here and a little potential here, so the element's going to want to move to lower potential. It gets absorbed by the light bulb, the energy goes into the bulb or whatever it is, and then it goes back to the beginning to get recharged again with more potential energy. Okay? I think I'll show you in the next section, or is it in this section? No, in the next section we'll go through a diagram of what this means. All right, so now we're going to take a moment to take a look at what's called Ohm's law. And this is where I was talking about the term ohmic a moment ago. So Ohm's law is very similar to Hooke's law. Remember Hooke's law was F equals negative kx? Well, it was 2 things multiplied equaling something else. Same idea here. So the voltage in a circuit is directly related to the current, I, and the resistance, R. That's what those stand for if you didn't know that. Okay, we went over current yesterday, so you should know now that I is current, but R is going to be resistance. So the voltage equals the current times the resistance. Now, your units for current yesterday were amperes or amps. The unit for voltage is just volts. That's an easy one to remember. Voltage, volts. But the unit for resistance is the one that people have difficulty remembering. It's called ohms. It's where it comes from Ohm's law. Okay? Ohmic, Ohm's law, ohms are units. The symbol for ohms, what is that symbol?
Omega.
What is it?
Omega.
Omega. Okay? Capital omega. Lowercase omega was that little w we used for frequency. Remember we looked at the frequency of a wavelength? There was a little w, that was omega, but a lowercase omega. This is capital omega times capital A equals capital V. Ohms times amps equals volts. Okay? Now, let me think of the slide first. No. Okay. In electrical circuits, the idea is that the resistance of something is usually determined, and it's a property of something. So for the most part, a lot of people solve for R, and they say R is the ratio of V to I. So if you have a material and you want to determine its electrical resistance, how much resistance it has to the flow in the circuit, you can apply a voltage to it and measure the current. Or you can apply a known current, if you know the current going through it, and measure the voltage drop. And we're going to do that in this class. We're going to do a little circuitry in chapter 20. In one of our labs, you guys are going to have to connect wires, hook up wires, use an ammeter to measure the voltage drop between things. And maybe actually even this, if I can come up with a lab for next week, maybe we'll do it with this chapter too. But the idea is that if you have some sort of an object that's a resistor, by the way, a resistor is anything that slows down the flow or controls it, or anything that even uses energy. A light bulb is a resistor. Okay, it actually slows down the flow and it uses up all that energy, and then the flow continues afterwards. So if you want to measure the resistance of any appliance, a microwave, an air conditioner, a light bulb, anything, you can measure the voltage and the current that are flowing. The current flows through it, you would measure the difference in the voltage. So before the energy flows through the resistor, you're going to have some voltage. Afterward, you're going to have a different voltage. The difference in that voltage is what is going in for the numerator here. The amount of current flowing through the actual wire is going to be the same anywhere. So you can measure that current anywhere. You can measure the voltage drop, okay, the potential difference, the voltage drop here. Divide these two and you'll get the resistance of that element. Now, obviously you wouldn't be doing this for everyday elements, they're specified. So when you buy something, you can determine on the label, it tells you the actual internal resistance, it tells you the voltage necessary, it tells you the current that it should run at. You're not going to actually measure a lot of this kind of stuff. But if you become like an electrical engineer and you actually set up a circuit in someone's house, you set up their electrical system in the house, then you actually need to do this kind of stuff. Okay? But the idea is that the resistance of an object is the voltage across the object over the current running through it. Okay? Now, in the class, we're going to use mathematics with, this formula here at the top, but you could really use either one, obviously, because one is just solved for the other. Okay, but this is the one that's given on your formula sheet. V equals IR. All right. Is that although Ohm's law shows us that there's a direct variation between V and I and R, like as I goes up, V goes up, or as R goes up, V goes up, what we're going to see here is that it's actually only valid for certain materials. Not all materials are considered ohmic. So ohmic materials, they have a constant resistance the whole time. For example, it's hard to do in here because we don't have it. But if I just turn on this light switch, this light's going to go on. It's got a certain resistance to it. It's not going to change. I turn it off, it has no flow going through it. Now, how many of you at home have some sort of a knob by your light switch or a lever?
I have like the thing where you press it and then it has a little dot and it goes
And
in.
you keep tapping the dots and move it up and down. Yeah, same idea. So it's a lever, it's a sliding lever, a rotating knob, or something you press. Now, what's happening there is you're changing the resistance, actually, of that appliance as you change the amount of electricity that's not electricity. Yeah, the amount of electricity that's flowing through the actual appliance. So when you turn that knob, you're changing its internal resistance. So these graphs are just showing you, if you look at this carefully, you've got current, you've got voltage, current, voltage. If you look at the ratio of current to voltage, current over voltage is 1 over R, because remember in the last slide, in the previous slide, we wrote this down. Right, we wrote that down in the previous slide, that resistance is voltage over current. So if I'm looking, these graphs are from your text. If I'm looking at current to voltage here, I can see that the whole way, this has a constant slope, right? Well, R is really like the slope. In this case, it's 1 over R. But think about this. This is like changing Y over changing X. Delta Y over delta X. That's how I think about this. The axes are rotated, though. But the constant slope indicates that this resistance is the same throughout. Here, what you're seeing is that the slope here is some number, then it gets more steep, it gets more steep, it gets more steep, it gets more steep. This would be an example of something where the voltage is changing. Okay, where the voltage is changing. Let's see. An example, okay, specifically besides what I was giving you, something called a diode. A diode is a mechanism that controls the direction of the flow. A diode can just switch the direction of flow instantly. So when that happens, the actual resistance changes. Okay, so that's one of the examples of something that would change this. The best example, honestly, is what I've been talking about. It's called a pentiometer. I'll define that, I think, in a moment. It's called a pentiometer. I want to pause for a second and show you guys a quick simulation. Now that we've looked at like a simple circuit and seen what's physically happening inside of a wire, inside of a battery, let's look at things that really affect the resistance and try to make sense of this. The easiest one to start with, to me, honestly, is the second one. The second one. Cross-sectional area. Think about a pipe. We talked about this the other day. Remember the gross example I gave yesterday? The waste pipe in your house? Unfortunately, it is. All of those pipes come together, and they have all this flow coming together. As a result, there's a bigger pipe that absorbs, that takes on all of the flow from those other three pipes. A bigger pipe would have less resistance. Why? Logically. It doesn't have to be mathematically. Sure?
Well, because it's easier for the flow of water to go through it.
Yeah. Like, think about it. The more water you have, right, going through a pipe, the more resistance there's going to be. Well, if you just increase the size of the pipe, you have less water relative to the pipe size suddenly. So the water will flow a lot easier. So number 2 is probably the easiest one to consider. This first one is the toughest one, probably. The third one is nothing you can do. It's the material. Some materials have higher resistance than others. That's it. Simply. Okay? For example, there's very little resistance to copper. So we have copper wires everywhere. It's also cheap. Copper is very cheap. Gold is a better conductor, actually. But are you going to make wires out of gold? No. It's much less abundant on Earth. So it's much more expensive. Copper is very abundant on Earth. So it's very little cost. The copper is a very low resistor, so it's used widely. Iron is not used much as a resistor. As a wire, sorry. The length of the wire, though, makes sense. And read what's in parentheses. Remember, more resistance is really just more collisions. Do you have more collisions in a shorter wire or a longer wire? Clearly a longer wire. A shorter wire here, those charge carriers are hitting less atoms, less metallic atoms. Now you got a wire this long, those charge carriers are going to hit a lot more atoms along the way. Okay, so the longer the wire, the greater the resistance. Those are, what do you say those are related? How are they related? Directly. So the first one here, you can write directly related. The second one, what are you going to write? What are you going to write for the second one? First one is directly related. How about the second one for cross-sectional area?
Indirectly?
Why on it?
I honestly just said the opposite.
I had a feeling. Give me some reasoning though. Now, think about what we just talked about. Remember the pipe flow example?
Because of
A pipe is really small, right? The water can't get through. Suddenly, it's a much bigger pipe. The water goes through a lot easier, right? So you said that they're indirectly related. So make sense of that. Look at your statements. As the area does what happens?
As the area like increases the width, like also. Oh no, when the area increases. No, okay. So when the width.
Go from here to here. As the
Oh, okay,
area-
I got it. When it's more like when there's so if it's shorter and wider, it becomes longer and not as wide.
Okay, that's a good idea. So, but specifically, forget the length of it. Just look here. As the area goes from a large area to a small area, the resistance goes from low to high, right? That's why they're indirectly related. As this decreases, the resistance is increasing. Okay, so part 2 is indirectly related there. Third one, obviously, there's no relationship of direct or indirect. It's material property. This last one is hard to see because you really can't see the thermometer, but this is the thermometer here. This thermometer is lower, this thermometer is a higher reading. So what could you say about temperature?
That the more temperature, the more resistance.
Okay? More temperature, more resistance. More temperature, more resistance. So if your computer is heating up, it has to do a lot more work to get that electrical flow through it. Because the resistance of those internal elements, when they start to heat up, becomes much, much greater. There's a lot more resistance. Okay, those are the 4 ideas that we're going to look at that affect resistance in general. Quickly, let's look at an example. The resistance of an air conditioner is 21 ohms. What is the current in the air conditioner when it's connected across a potential difference of 115 volts? Well, right away, potential difference means voltage. If you didn't know that, just look at the units. 115 volts. This is one of the few items whose variable and unit are identical. You see that? The variable for voltage is V, the unit is also V. It's one of the few times that that happens ever. Resistance is 21 ohms. Question is, find the current. Simple, simple, simple math. You're noticing more and more, by the way, that a lot of the math with electricity is easier simply because the real heavy math with electricity is all calculus math. A lot of electricity with physics has to do with a lot of calculus-based math. So if you want to study that and you enjoy this kind of stuff, or you think you might in college, you're going to take calculus before you would take an electrical engineering course. Because all the math you would do in electrical engineering would all be calculus-based. So the math we're going to look at is relatively simple because it's algebraic. Start with Ohm's law. Since we're looking for the current, let's go ahead and solve for I. The voltage over the resistance, 115 over 21. Okay, we're going to get
5.5 amps.
that works. 5.5 amps. Okay, 5.5 amps. All right, the last thing I want to talk about. Oh, fun fact. That's just why I have my notes in front of me. I have these random facts I write down. Forgot about this. So, how many of you have seen Meet the Parents?
Yeah.
Or Meet the Fockers? Meet the Parents? Okay.
Yeah.
So the original one, Meet the Parents, Robert De Niro is like this crazy, overbearing dad. He's very protective of his daughters, remember? Do you remember what he hooks up Greg to?
Lie detector?
Yeah, a lie detector. And he hooks him up to this machine, right? So what's interesting about a lie detector, it measures a lot of stuff. Now, one of the things about a lie detector that it uses is actually the sweat on your body. So a lot of people, when they lie, they start to perspire. Like right away, if somebody's lying to you, you see like sweat building, you think that they're like, what are they saying? What's going on? You can read people like that. That's what he is in the movie. He's like a human lie detector. But sweat produces fluid on your body. The fluid has salt in it. Salt is an electrolyte when in fluid. So actually, when you hook up these nodes to your body, it's measuring the current flowing through your body. Like it's putting a little bit of voltage to your body to the point where it's not going to hurt your body at all. And it measures the current. It's a minimal amount. But the minute it sees a current change, the current changing is also showing that you're lying. Okay, that you're starting to sweat. And they'll see that when somebody lies naturally, that they'll sweat and they'll see the current flowing through their body completely change. So that salt that's in the water on your skin when you're sweating is what's giving you away for a lie detector. So when people that are like in the armed forces they're trained to beat lie detectors. You know this, right? People are trained to beat the box, it's called. They do this because they don't want, if somebody gets captured in another country, to be able to like torture and interrogate them and get answers out of them. It's terrible, but it's the truth. So they're trained to keep their cool, to keep calm, because what happens, they don't sweat then as a result. Okay? Hey, last pentiometers. A pentiometer is a variable resistor. Remember that light switch that I was showing you earlier? There's a metal contact that changes the amount of contact between the parts and the elements in the circuit, which either increase or decrease the current. So a pentiometer, again, is a type of resistor, a variable resistor. Video games, joystick on your Xbox or PS3 or PS4, those joysticks are pentiometers. You move it up a little bit, you see the reticle move, right? You move it up a lot, you see the reticle jump, unless you're inverted, whichever. But you see it jump depending on the actual game. It's because it's a variable resistor, it changes as you push more. There we go. So superconductors, and we spoke about these with superconductors and semiconductors that day, are things that exhibit no resistance. So you could apply a current, right, and there's going to be no resistance in the wire. That current will continue forever. It will not stop. Whereas if you apply some sort of a current and then you remove the source of battery from it, it can't continue to be pushed forward. This is like the equivalent of having no friction at all, like a frictionless surface. So superconductors exhibit this zero-like resistance, pretty much zero, when they're below a critical temperature. That's the key point here. And if you recall what we talked about, we spoke about temperature and how temperature affects your resistivity of the materials. So copper at a higher temperature versus a lower temperature has a different resistance. Well, this is what's happening here. So below this temperature, in this case, what are kelvins, by the way? We haven't really talked about that yet. We will later in the year, but from chemistry.
So you measure temperature.
Yeah, it's like the Celsius measurement, but it's for the absolute scale. So 0 Kelvin is the lowest temperature that's possible. It's not even possible, really. We'll talk about that later, how you can't ever actually achieve absolute zero. It's not possible. But you can get close to it, and we're really close, 4 degrees away from the coldest temperature that's possible to exist. 0 Kelvin is like the absence of any motion whatsoever for any molecules. Any molecule itself, even like this table, the atoms are vibrating at certain frequencies. That's why you hear a lot about string theory and these wave phenomena, because at a microscopic scale, things actually oscillate and vibrate. So remember we talked about a spring mass system and a pendulum? We talk about that because in physics they occur so much. So with this idea, there's no motion of the particles at all under a certain temperature. Almost none. When the particles aren't moving, there's no resistance because there's no interactions between the actual current that's traveling through the circuit and the particles themselves because of the lack of motion at this low temperature. Okay? So that was the last slide for this. Go on to